Hey everyone, welcome to my homework 4 for computational methods. This video series will be 3 parts, right? And the first part is going to be implement the NRTL activity coefficient model via Python loops, einsums, and matrix vector multiplications, and compare the result for all 3 implementations for an equimolar mixture of methanol, ethanol, water at 300 Kelvin. So real quick, let's find out NRTL. Let's see what it is. Chemical. It's a non-random two-liquid model that's you can use it for activity coefficients. So when you're doing stuff like Antoine's equation, Raoult's law, and it's not ideal and you need the activity coefficient, that's when you would use this, right? And so um, we're going to be uh, finding the activity coefficient by this method right here, these equations, using 3 ways: loops, einsum, and then matrix vector multiplication. So first things first, I have a couple things that um, we have to import. So we actually import some stuff from GitHub that lets us access NRTL databases for coefficient values, right? And then so these are the equations we have to use. We want to solve for this activity coefficient, so we're going to take the exponential of this quantity, this big quantity right here, but we need to figure out, um, we need to calculate all of the small quantities first, right? And so if we go back, our mixture is methanol, ethanol, and water, 300 Kelvin, and how do I say 300 Kelvin and equimolar. So, oh, sorry. Um, Let me move that out of the way. That was my practice run through. Okay, so I've made an array and then of methanol, ethanol, and water. X is NP array 1/3, 1/3, 1/3. T is 300, right? So I'm gonna go ahead and then define my function activity. Um, uh, I'm gonna call it activity loops, right? And it's gonna take an X and it's gonna take in the temperature, right? And then so my first thing is I want to find tau, right? So tau. And for our components, we're only going to worry about the B NRTL coefficient. So we're going to say tau equals NRTL, or P dot NRTL. So that will find the NRTL coefficients for methanol, ethanol, and water. Um, um, and then I'm going to divide, and then I'm going to put the temperature that I want, and then I'm going to divide by. No, sorry. I'm gonna do NRTL underscore B, and I'm gonna divide by temperature. Sorry, didn't mean to run it, but it's fine. And then for G, I'm gonna say it's the exponential of alpha times tau, right? So I'm gonna say it's NP dot exponential, right? Of should be negative. I can put the negative here. Negative P dot NRTL underscore alpha times tau, right? That we calculated last time. Okay, yeah, good. And then what we're gonna do, right, is I'm gonna do this out here real quick. So I'm gonna copy this. Here, I'm gonna check. Okay, yeah. Um, and then I'm going to run it. I'm gonna print tau. Right, so tau is a 3 by 3, or um, tau is a 3 by 3 matrix, right? And so I'm going to iterate through it and iterate through G, which is also going to be take on the shape of tau, along with X, which is 3 by 1, or 1 by 3, and then I'm going to compute all of these summations, right? So to do that, I'm going to define a couple arrays. I'm going to say xg, which is literally x times g. I'm going to say it's np, it's going to be, I'm just going to initialize it basically. I'm going to say it's an array of zeros that is like x, right? So it takes on the same size of x because it's going to be that. It's going to be x times g. Um, and then I'm also going to do one where it's going to be x tau g divided by xg, just to make it a little easier on me. X tau g divided by xg, and that's also going to have the same size as x. And then so that kind of if you divide those, you're going to get the left-hand side. And then term 2 is made up of xg's and x tau g divided by xg's, right? So what I'm going to do here is I'm going to say term 2, and it's going to have the same size if we're going to add them. Underscore like x, yeah? And then I'm going to say n equals x dot size because we're going to need it for our loops, right? So I'm going to say for I in range n. And then I want to do nested for loops because these are two-dimensional arrays. So I need to iterate through the rows and the columns, right? And what I'm going to do is for each column, which I believe represents each sort of component, I'm going to reinitialize x tau g as 0. And then I'm going to say x tau g plus equals, because it's a sum, and it's x times tau dot g. So it's x at j, because j um, loops through, sorry, j would loop through the number of columns. So yeah, xj times tau of j I times g j I. So remember, x tau g here is a scalar. So if you look at this, we're just kind of following this exact nomenclature, right? And then xg at j plus equals xj times g at j comma I, right? Now that makes a ton of sense. We're kind of just following exactly what we're doing here. And then if we're going to find x tau g divided by xg, it's just going to be, and it's I, because we're still iterating, right? So here we're going to be iterating column 1, column 2, column 3. Um, it's going to be equal to x tau g divided by xg at I, right? And that takes care of a couple of it. And now we have to do the term 2, right? Which is if we go up, it's this big guy right there, the type. Um, so I'm going to say I'm going to do my loops again. And then I want to basically make all of this as one term, and we're calling it term 2. So term 2 equals, and so how am I going to do this, right? What I'm going to do is I need the xg, and then the xg's, right? So the xg, the top one we've calculated. The denominator we've calculated. The numerator we have to figure out. So it's going to be xj times g at I comma j, right? And then we're going to divide by xg at j times, and then it's going to be tau. Let's go look, tau ij, right? Because I and j are just basically helping us, give it a second, yeah, go through the components. Ij minus, and then it's going to be exactly what this is, right? So um, x tau g div xg, right? So that's what that is, x tau g divided by xg. And then it's going to be at j. And then we're just going to return, right? We're going to return np.exponential term 2 plus x tau g div xg. So let's run this. And then let's actually run this activity loops x comma t. And we got a number. Let me pause it real quick and make sure that it's the correct that's the correct number that we want. All right, guys. So I'm back. I figured out what was wrong, and I had to take a little bathroom break, so it was a little two-in-one there. But basically, so if we think about this, right, for the xg here, if we look at our formula, the index that we should be indexing over is not j, right, but it should be I. This one should be I, and then the one that we were calculating down there, it was populating over j. So it, it should be xgi, and then if we run this activity loops, I think this is the number that we're looking for. And so the next part of this one, sorry, the next part of this one is, if you go to the, yeah, is implement functions, no, sorry, is to do this via einsum, right? And so what is einsum? It helps you kind of do matrix multiplication with higher dimensions, right? That's like the best way I could describe it. You lose a lot for like second order tensors or higher order tensors, I guess. But basically, if I type it, it'll make a lot more sense. So definition, I'm going to say activity einsum. I'm going to say x t, and then I still need these parts, right? Right, and then let's do x tau g. Now, what this is going to be is np.einsum, right? And then I guess I should type it out and then explain it. So what this is saying here is, right, I have x and I'm multiplying by tau g. That's what the times g. That's what the last part is, right? And basically I have a matrix, right? Axis j. Um, I want these matrices to be multiplied across axis j, and then I want them to be summed on that j column as well. And then I want its final size to be the size of I. And so I'm doing that because I want because I want to like how we did it here, right? We summed all of j comma i's for the x tau g. So I want to mimic that here, which is why I'm summing on column J, right? And so for xg, I'm going to do np.einsum, and then I'm going to say j, ji, and I don't care about the size, because the size is going to be the same. If you don't specify the size, it's going to just be the same. I'm going to say x and g, because here we were summing across the j's as well. It's the same idea, right? And then so x tau g div g is just these two things divided. And then I need to get the term 2, right? The pesky little term 2. So term 2 equals np.einsum, and then what am I summing? How am I going to do this? I mean, it's going to be j, of course. And then I want to sum across the I-axis this time, not the j-axis. And then I want this to go, you know, looking for the, yeah. I want this to go to I. And then, so what am I going to multiply here? So let's pick x again, because x has axis j, or g. And then I'm going to do the rest of this. So it's going to be g, oh gosh, this is going to be rough. It's going to be g times tau minus, and then what is it? Oh, x tau g over xg, right? So tau minus x tau g div g, and then you're going to divide that, oh sorry, x tau g div g, um, and it's not all of it, right? I want just the jth column. Oh, I just want, sorry, that was a poor way of explaining it. And then divided by xg. But I just want the columns. That's what I was trying to say. Just how we did it in the previous one, right? And then I'm gonna return the exact same thing. And then let's run our activity loops and activity einsum. It's not return. Oh, did I forget a parenthesis? Yeah, a little bit. Name x tau g div. Oh, it should be just div g. Wait, yeah, wait no. X tau t div xg. Okay, yeah, this should be xg here and then xg. Okay, and then yeah, so this should. Here we go, but they're not super accurate, which makes me think something's wrong in the loops, right? Um, I mean they're pretty close together, I think. But I'm fairly certain that these should just be swapped, because then they would be accurate almost all the way. Um, so somewhere where I was summing tau ij minus x tau div g g, this should be I. No, this should also be I. Let's see. All right, guys. It actually took me a really long time to figure this out, but it was just that I wasn't summing my term too. So it's a summation, so we should sum it. I mean, that makes sense. Um, oh, not for the activity on sum. It was the for the loops. I forgot that I needed to sum it like this. Okay, so there we go. And then the last way we're going to do this is multiplication, matrix vector multiplication. So I'm going to say activity matvec xt, right? And then these two guys, they're the easiest part of our code, right? And then, so what we're going to do actually is we're going to resize x so we can multiply it. So I'm going to say x equals x dot resize 1 negative 1. Let me just say print x. Oh, stop that. Just say print x, and then I'm going to call the activity matvec function. Oh, sorry, it should be in parentheses, not in brackets, because we're making matrix. Um, let's see, because I'm pretty sure you can do it like this. Mm, it says type mismatch. Oh, their sizes should match, right? X equals x dot resize. But all I want to do here is give me a second. Let me check my notes real quick. All right, it was because I was using the wrong function. That's my bad. I should be using reshape, which now I can reshape this x. And so if I print it, it's one. It has an array inside of an array, and it's one dimension, right? And you're going to see how this helps us because then we can do matrix vector multiplication. Um, so x tau g equals x. Um, it's x at, because tau and g are the same dimensions. So now let's see if I can print. Sorry, if I can print, you know, x tau g. Let's see what that looks like. There you go. It's maintained the same size. It's 3 by 1. This is exactly what we were hoping to do. And so let's say xg equals x at g. Right now, the rest of this kind of writes itself. So x tau x tau g div xg equals x tau g divided by xg, right? And then I'm going to say my term 2, right? Term 2 equals, and then I can't actually remember that formula even though I've used it so many times. Okay, yeah. It's going to be x at g times tau minus x tau g div g, x tau g div xg, yeah. And then I want it like this, but I want it in brackets, right? Divided by xg, by xg. And then I'm basically ready, right? I'm just gonna say return np.exponential x tau g div xg plus term 2. Oh, hold on. What is this? Right? So you might have thought that would work, but now we're getting a really, really like it's still 1 by 1 matrix, but it's like a 3 by 3 matrix as one array. And so we have to fix that. And I mean, obviously we have to fix it, right? And the way that we're going to do that is we're going to say return, oh, I should have just kept all of these, term 2 at x dot squeeze, right? And what does dot squeeze do? So I have this pulled up, numpy dot squeeze. It'll take out all the little arrays and just make it, um, so like squeeze. So I don't want it to be squeeze dot shape. So the shape of it will become 3 1. Basically, it'll how do I say? It'll just kind of expand. It's not the same thing as flatten, but it's hard. mm, it's hard to say. But basically, if I we'll get an array of just one one row. So if I do this and then run it, it says invalid syntax. It should be because of this. USB device not recognized. And then we also want to flatten it. So what I'm going to do here is I'm going to say my answer equals this. And then I'm going to say return numpy.exp. And I'm going to say answer.flatten. And there you go. This is how to code the activity matrix vector, use matrix multiplication, activity loops, and activity einsum. I'll see you guys in the next part. Thanks. Goodbye.